Hey everyone, welcome back. Today we're going to be tackling something that might sound a little dry at first. Decarbonizing buildings.
Okay.
But trust me, it's way more exciting than it sounds.
Yeah.
And before you tune out thinking, why should I care about buildings? Let me drop a knowledge bomb.
Okay.
They're responsible for nearly 40% of global emissions.
Wow.
So yeah, what we do with our buildings is a big deal.
It is. And we're going to unpack some seriously cool tech and strategies for making those buildings more sustainable.
We've got excerpts from a couple of in-depth reports to guide us.
Right.
And we're putting the spotlight on heat pumps.
Yeah, those are all the rage right now.
They are, but we're going beyond just the basics.
Absolutely.
This deep dive is for you if you're thinking about making your own building more eco-friendly, maybe even retrofitting an older one.
Right.
Or if you're just curious about how we can actually slash those emissions.
Exactly. The goal is to arm you with a solid understanding of heat pumps.
Yeah.
What they can do.
And what to consider if you're thinking about using one.
Okay, let's dive in. First things first. What exactly is a heat pump?
Sure.
They seem almost magical, like they can heat and core at the same time.
Yeah.
Is that even possible?
It is possible. Think of a heat pump as a two-way street for heat.
Okay.
It can move heat from one place to another.
Okay.
Unlike your furnace, which just blasts heat.
Right.
Or your AC, which just makes cold.
Right.
And get this, it does all this with crazy efficiency.
So it can heat and day? Cool.
It can.
Okay, color me impressed.
Yeah.
But how efficient are we talking here?
Well, heat pumps are measured by something called coefficient of performance. Or COP for short.
Okay.
A COP of 2 to 5 is pretty typical. That means for every unit of energy it uses, it can pump out 2 to 5 units of heat.
Wow.
Compare that to electric resistance heating, which only has a COP of 1.
Wait, a COP of 5?
Yeah.
So that means a heat pump could be 5 times more efficient than just using electric heating.
Suddenly, this isn't sounding so dry anymore.
You got it. And that efficiency translates into lower energy bills.
Right.
And a smaller carbon footprint.
Okay. I'm sold on the efficiency thing.
Good.
But let's say I'm picturing this for my own building.
Okay.
How do I figure out what size heat pump I need?
You've got to think about both heating and cooling needs.
Okay.
You want a heat pump that can handle the higher of the two loads, whether that's heating or cooling, to avoid relying on less efficient backup systems.
So if I need 5 tons of cooling, but 6 tons of heating, I go with the bigger one, a 6-ton heat pump.
You got it.
So it's oversized for cooling just to handle those peak heating times.
Right.
Is that always the most efficient choice?
That's a great question, and it depends on several factors, including the climate, the building's insulation, and even your energy rates.
Yeah.
It might be worth considering a slightly smaller heat pump with a high-efficiency backup system for those extreme days.
Good point. It's not a one-size-fits-all situation.
Right.
Now, are all heat pumps created equal?
Good question. Not all heat pumps are the same.
Okay.
You've got 2 main types, air source and water source.
Okay.
Air source heat pumps pull heat from the outside air.
Okay, that makes sense.
Yeah.
What about on those super cold days when the air is practically frozen?
Right.
Can those air source pumps still pull out enough heat?
That's a common concern.
Yeah.
It's true that their capacity drops off as the temperature plummets, which is something to consider in colder climates.
Right.
But here's a cool detail.
Okay.
Newer models use variable speed compressors, allowing them to work efficiently even when it's chilly out.
Ah, so technology to the rescue. So what about those water source pumps?
Yeah.
Where do they get their heat?
They use water as their heat source, whether it's from a well, a lake, or even a geothermal loop.
So they're tapping into a more stable temperature source?
Right.
That makes sense?
Yeah.
But I'm guessing air source heat pumps are more common, right?
You're absolutely right.
Okay.
Air source pumps are more widely used, partly because they're easier and less expensive to install.
I remember those old air source pumps needing a ton of help from backup heating systems.
Yeah.
Is that still the case?
Not really. Older models did rely heavily on backup.
Right.
But newer designs are much better at providing heat at lower temperatures.
Okay.
That means less need for those less efficient backup systems.
That's great news. And I heard there's this amazing trick
Yeah.
where air source pumps can actually recover heat from a building's exhaust air. Is that for real?
It is. Some air source heat pumps can grab that heat from the exhaust and use it to heat the incoming air.
Good, yep.
It's like giving your building a little energy recycling boost.
Whoa, wait. So you're saying my building's stale air can actually H-E-L-P heat the place?
It can.
That's mind-blowing.
Yeah.
Okay, we've covered the basics of what a heat pump is.
Right.
And the different types. Now, how do you actually install one? What are the different designs?
You have two main architectures.
Okay.
Centralized and distributed.
Okay.
A centralized system is like your traditional HVAC setup. One big unit handles the whole building.
Okay. One unit to rule them all.
Right.
What about the other option?
Distributed systems use multiple smaller units spread throughout the building.
Okay.
Think of it like each zone having its own mini heat pump.
Okay.
This can be a game changer in larger buildings, especially those with multiple tenants, like an office building.
Oh, right.
Yeah.
So imagine an office building with lots of different tenants. A distributed system lets each tenant control their own heating and cooling.
Right.
Which means no more thermostat wars.
Exactly.
Speaking from experience, that alone might be worth the upgrade.
It not only improves comfort,
Right.
but can also increase efficiency since each zone is only conditioning the space that needs it.
I could see how that would be a big win. Yeah. Now, I'm curious, can you integrate heat pumps with other building systems? Like, could they work together with other cool tech to make the whole building even more efficient?
You bet. You can integrate heat pumps with things like absorption chillers,
Okay.
which use heat rather than electricity to power their cooling cycle. This is especially cool if you've got access to waste heat, like in a factory.
Oh, right. It's like turning waste into a resource. So instead of that heat just disappearing, it helps cool the building.
Right.
That's some next level efficiency.
It is.
What else can you do?
Another option is a heat reclaim chiller.
Okay.
These systems capture the heat normally lost during the cooling process and use it to provide hot water or even heat the building.
So it's like you're recycling heat that would have just been wasted.
Exactly.
I like it. Where would these heat reclaim chillers be most useful?
They're especially helpful in buildings with high simultaneous heating and cooling loads.
Okay.
Like a hotel where guests use both heating and cooling throughout the day.
That makes sense.
Yeah.
Okay, we've talked about using air.
Right.
And even waste heat. But what about water as a way to move heat around?
You're talking about ambient water lukes?
Okay.
They use a network of pipes filled with water to move heat from a central heat pump system to individual spaces in the building.
Right.
It's like a building-wide radiator system, but with more control.
That's a good question. It sounds pretty efficient.
Yeah.
But are there any downsides to this water loop system?
One thing to consider is that you might need supplemental heating or cooling to keep the water at the right temperature, especially in extreme weather.
Right.
So you might need cooling towers in hot weather and supplemental heaters when it's freezing out.
Okay, so there's some complexities to consider.
Right.
But I'm all about exploring cool tech. What about thermal storage?
Sure.
It sounds almost futuristic. How can you use that with heat pumps?
Thermal storage is basically a giant battery for heat and cold.
Okay.
You use a big tank to store either hot or cold water, and then you tap into that stored energy when you need it.
Right.
It's like a giant thermal battery.
Okay.
Pretty neat.
That's neat.
Yeah.
It's like having a reservoir of heating and cooling power ready to go.
Exactly.
But what are the benefits of this giant thermal battery setup?
Here's a fascinating fact.
Okay.
Thermal storage can often help you use smaller heat pump equipment by smoothing out those peak loads.
Right.
It can potentially reduce equipment size by up to 20%.
Hold on. So you're telling me I could potentially get away with a smaller, less expensive heat pump just by adding this thermal storage tank?
You could.
That's incredible.
It makes the system more efficient overall.
Right.
And can lower those upfront costs.
Okay, I'm definitely adding thermal storage to my wish list.
Good idea.
We've been focusing on new construction. But what if I want to retrofit an existing building? Are there any special challenges to consider?
Retrofit projects definitely come with their own unique set of challenges.
Okay.
It's super important to thoroughly evaluate the building before making any decisions.
Right.
We always recommend taking a top-down approach.
Right.
Starting with the big picture and then drilling down into the details.
So you figure out your overall goals for the building.
Right.
And then get into the specifics.
Exactly.
What are some key things to consider during that initial evaluation?
You need to make sure the existing electrical infrastructure can handle a new heat pump system.
Okay.
Especially for those air source pumps.
Right.
You don't want to be halfway through the project and realize you need a major electrical upgrade.
Ugh, that would be a nightmare. Cost overruns and delays.
Yeah.
No thanks. So electrical capacity is a big one.
Definitely.
What else should you look at?
You also need to check out the building envelope.
Okay.
Things like insulation and air sealing. Even simple improvements in these areas can make a huge difference in your heating and cooling needs.
So you're saying that improving the building's shell could actually make the heat pump system more efficient.
It could.
And potentially reduce the project's overall cost.
Right.
That's a win-win.
Precisely. It's not just about the heat pump itself. You need to consider the whole building. Even seemingly minor improvements can have a ripple effect, leading to greater efficiency and lower costs.
This is all incredibly helpful. Now, I know our source material included some real-world examples of how all these concepts come together. Are you game to walk through those?
Absolutely. Let's take a look at what they call solution pathways for retrofitting a commercial building.
Perfect. This will give us a chance to see how all these pieces fit together in a real-world scenario.
Right.
What's the first pathway?
Pathway 1 focuses on keeping the existing air conditioning units for cooling and adding a new air-to-water heat pump system for heating. This often incorporates radiant heaters, which provide really comfortable warmth.
Ooh, radiant heat. That sounds cozy. So no more drafty forced air blowing around.
Right.
Sign me up. What are the key considerations for this pathway?
You need to be sure your electrical system can handle the new heat pump.
Okay.
And you might want to look into energy storage to minimize reliance on backup heat.
Okay, so you're keeping the old AC but adding a new heating system. What about pathway 2? What's the strategy there?
Pathway 2 involves a more complete overhaul.
Okay.
You replace those old rooftop units with heat pump RTUs and add a dedicated outdoor air system for ventilation. Basically, you're creating a system designed from the ground up with heat pumps at its core.
So it's a more comprehensive approach, but probably more efficient in the long run.
Exactly. And with this pathway, it's super important to choose cold climate heat pumps to minimize the need for backup heat.
Right.
You want a system that can handle those cold snaps on its own.
Makes total sense. And heat recovery ventilation would be essential in this setup, right?
Absolutely. You want to preheat or pre-cool that incoming air.
Okay.
Minimizing the work the heat pump has to do and maximizing efficiency.
Right. It's all about squeezing out every bit of efficiency we can.
Yep.
So we've got two very different pathways, both focused on harnessing the power of heat pumps.
Right.
Now, no matter which pathway you choose,
Yeah.
proper installation is crucial.
Absolutely.
Any final thoughts on installation best practices?
One thing I can't stress enough is eliminating refrigerant leaks.
Okay.
Not only is it bad for the environment, but it also sabotages efficiency.
Right. Leaks equal waste, not good. What about keeping tabs on how the system is performing once it's up and running?
Submetering is key.
Okay.
By tracking energy consumption,
Right.
you can monitor how the system is performing and identify areas for improvement.
Okay.
It's like giving your building an energy checkup.
Love that. You're basically gathering data to fine-tune the system and make sure it's running at peak performance.
Right.
And what about the existing heating system?
Yeah.
Should you just rip it out and replace it?
I'd say hang on to it.
Okay.
It can be a valuable backup in case of extreme weather or if the new system has any hiccups.
Okay.
It's like having an insurance policy for your building's comfort.
That's a smart move. Always good to have a backup plan.
Yeah.
Wow. That was a ton of information. We've covered so much ground, but I feel like we're just getting started.
I know, right?
Before we jump to the next part, I need a minute to process all this.
Me too. And when we come back, we'll shift gears a bit
Okay.
and look at something that might seem totally unrelated to buildings.
Okay.
International shipping.
Wait, shipping. How does that tie into all of this? I'm intrigued.
You'll have to wait and see.
But for now, I need to grab a refill and let all this new knowledge sink in.
Okay, sounds good.
We'll be right back.
See you soon. Welcome back. I hope you've got your thinking caps on because we're about to dive even deeper into the world of making buildings more energy efficient.
I'm ready. We were just talking about how crucial it is to have a good installation for a heat pump system,
Right.
especially preventing refrigerant leaks.
Right. And remember, those leaks aren't just bad for the environment.
Yeah.
They also make the system less efficient,
Right.
which means you end up paying more for energy.
Okay, so a leaky system is a money-wasting system.
Exactly.
Got it.
Oh.
Now, I know we talked about how efficient heat pumps are, but I've always been curious about the magic behind how they actually work.
Yeah.
I remember you mentioned something about COP earlier. Can you break down that whole coefficient of performance thing?
Sure.
In a way that even I can understand.
Absolutely. Think of COP like this.
Okay.
It's a measure of how much heat you get out
Okay.
for every unit of energy you put in.
Okay.
A higher COP means more bang for your buck.
Right.
So a heat pump with a COP of 3 means you're getting 3 units of heat
Okay.
for every unit of electricity you use.
Okay, that makes sense.
Yeah.
It's like a measure of how effectively it's moving that heat around.
Exactly.
But what's happening inside the heat pump to make that happen?
At the heart of it all is the compressor.
Okay.
That's the muscle of the system.
Right.
And the most common type these days is the scroll compressor.
Scroll compressor. Why does that name sound familiar?
They're used in all sorts of things.
Okay.
Refrigerators, air conditioners, even some car engines.
Okay.
They use a spiral motion to compress the refrigerant, which is much smoother and quieter than older compressor types.
Ah, so they're more efficient and quieter.
Yep.
I can see why they're so popular.
Right.
But what's actually happening to that refrigerant?
Well, the refrigerant goes through these special coils called heat exchangers.
Okay.
There's an evaporator and a condenser.
Right.
And they're where the real magic happens.
Okay, this is where I usually get lost. So break it down for me. What are these heat exchangers doing?
Imagine them like little radiators. The evaporator absorbs heat from the air or water, and the condenser releases that heat into the space you're trying to heat.
So the refrigerant is like a little heat shuttle, picking up heat in one place and dropping it off in another.
Exactly.
I'm starting to get the picture.
Good.
Exactly. It's this continuous loop of absorbing and releasing heat that makes it possible to both heat and cool your building.
Right.
Using the same system.
Right.
Okay, I feel like I just had an aha moment.
Great.
All those years of wondering how heat pumps worked, and now I finally get it.
I'm glad to hear it.
Thanks for demystifying that for me.
Happy to help. Now let's shift gears a bit and talk about another key piece of the building decarbonization puzzle.
Okay.
Reducing the energy your building uses in the first place.
Okay.
It's not just about what kind of heating and cooling system you have. It's about making the building itself more efficient.
You're talking about reducing those internal loads,
exactly.
Right? I know our source materials emphasize that.
When we talk about evaluating existing building conditions, one helpful approach is to think top-down.
Okay.
Starting with big picture information.
Right.
And then getting into the specifics of how the building actually operates.
So you start with the bird's eye view. And then zoom in on the details.
Exactly.
What kind of big picture stuff are we talking about?
Sure.
Give me an example.
For starters, you want to know what type of building it is.
Okay.
How big it is, how many people use it, and what the operating hours are.
Okay.
Think of it like getting a general profile of the building.
Okay, that makes sense.
Yeah.
It's like gathering basic intel before you go on a mission.
Right.
And once you have that overview, you can start digging deeper.
Precisely. You want to assess the building's systems. And one of the first things to check is the electrical infrastructure.
Right.
Can it handle a new heat pump system?
Yeah.
This is especially crucial for air source heat pumps.
Right.
Which can draw a lot of power.
Right. We talked about those potential electrical upgrade costs earlier.
Yeah.
Better to know that up front than get hit with a surprise later on.
Definitely.
What other things might affect how much energy a building uses?
Lighting is a big one.
Okay.
You want to know the lighting power density, or LPD, for each type of space in the building.
Okay.
That basically tells you how much power your lights are using per square foot of space.
Okay, so you're measuring how much light you're getting.
Right.
For the energy you're putting in.
Exactly.
And if it's not so efficient, what can you do about it?
Well, there's the obvious stuff, like switching to more efficient LED bulbs.
Right.
But it goes beyond that.
Okay.
You can use daylighting controls that dim the lights when there's enough sunlight streaming in, and occupancy sensors that turn off lights when nobody's around.
So smart. I love those occupancy sensors.
Yeah.
They make me feel like the building is paying attention and saving energy, even when I forget.
Right.
What about all those devices that are plugged in all the time?
Yeah.
Computers, printers, coffee makers. I feel like those can be a silent energy drain.
You're right. Those are called plug loads.
Okay.
And they can add up.
Yeah.
Unplugging things when you're not using them is always a good idea.
Right.
But there are also smarter solutions.
Okay.
Like advanced power strips that can automatically cut power to devices when they're not in use.
So imagine a system that automatically shuts down your computer monitor when you leave your desk.
Right.
Or powers down the printer after hours. That could save a lot of energy.
It could.
Especially in a big office building.
Exactly. And these systems can also help you identify which devices are the biggest energy hogs.
Right.
So you can target your efficiency efforts more strategically.
This is all so fascinating. It really makes you think about how much energy we waste.
Yeah.
Without even realizing it.
Definitely.
But I want to circle back to something we touched on earlier.
Okay.
Cost effectiveness.
Sure.
I know that incorporating all this cool tech and making these upgrades can be expensive.
It can.
How can we make sure these decarbonization efforts are actually affordable?
That's the million-dollar question, right? And one of the biggest factors is something called the levelized cost of production.
Okay.
Or LCO for clean energy technologies.
LZOP. Refresh my memory. What exactly is that?
Think of it as the average cost of producing something.
Okay.
Like a solar panel or a battery. Over its entire lifetime.
Okay.
It includes everything.
Okay.
The initial cost,
Yeah.
the operating expenses, even the cost of financing.
Right.
It gives you a way to compare the costs of different energy technologies, apples to apples.
Okay, so it's a way to see how the cost of clean energy stacks up against those dirty fossil fuels over the long haul.
Right.
And what have we learned about LCOPs for clean energy?
The good news is that LCOPs for a lot of clean technologies have been dropping dramatically in recent years, making them more and more competitive with fossil fuel.
That's what I like to hear.
Yeah.
So as those clean technologies become more affordable, it makes even more sense to ditch those fossil fuels.
Absolutely.
What's driving that downward trend in LCOPs?
Well, energy costs are a big factor. The price of electricity, which is the main ingredient for a lot of clean tech manufacturing, can vary a lot from region to region. And material costs matter too. But they tend to be less unpredictable than energy prices.
So if you can make those clean energy technologies in a place with cheap electricity, you're going to have a lower LC hop, which makes those technologies more competitive in the market.
Exactly.
It's all about finding the sweet spot for production. But what about government policies? Don't those play a role in all of this?
Absolutely. Governments can create policies that directly support clean energy manufacturing, like tax breaks, subsidies, and grants. These incentives can help level the playing field and make those clean technologies more attractive to investors.
So governments are putting their money where their mouth is and supporting the growth of the clean energy industry.
They are.
I like it. What are some other policy tools that can make a difference?
There are also indirect measures, like carbon pricing, which makes it more expensive to pollute. And renewable energy mandates, which require utilities to get a certain percentage of their power from clean sources.
So these policies are basically creating a market where clean energy can thrive. And it's not just about cost, right? It's also about security and resilience.
Exactly. By diversifying energy sources and supporting domestic clean energy manufacturing. Countries can reduce their dependence on those shaky global markets and geopolitical rivals. It's about creating a more stable and secure energy future.
It's like a triple win.
Yeah.
Cleaner energy, more energy independence, and a boost for the domestic economy.
It is.
I'm all about that.
Good.
We've talked a lot about the global picture, but I'm curious about those regions that are still developing their economies. What challenges and opportunities do they face when it comes to clean energy?
That's a great question. Emerging markets have a crucial role to play in the clean energy transition, both as producers and consumers of these technologies. But they also face some unique hurdles.
Like what? What's standing in their way?
Many emerging markets lack the infrastructure, the financial resources, and even the skilled workforce needed to build a strong clean energy industry. And they often struggle to compete with established players, like China, that have had years of government support and economies of scale.
So it's a classic catch-22. They need investment to develop the industry. But it's hard to attract investment without having that solid foundation in place.
Right.
How do they break out of that cycle?
That's where international cooperation comes in. Advanced economies can play a huge role by providing financial assistance, helping with technology transfer, and building capacity in those emerging markets.
So it's about sharing knowledge, resources, and expertise to help those emerging markets leapfrog those dirty fossil fuels and embrace a cleaner future.
Exactly.
I love that idea of leapfrogging, skipping over those outdated technologies and going straight to the good stuff.
And it's not just about altruism. It's in everyone's best interest to support the clean energy transition globally. A world powered by clean energy means less pollution, a more stable climate, and more economic opportunities for everyone.
It's a win-win for the planet and the global economy.
It is.
Okay, we've covered a lot of ground today.
We have.
From the inner workings of heat pumps to the global forces shaping the clean energy transition.
Yeah.
It's mind-blowing to think about how all these pieces connect.
It really is. And it highlights the importance of thinking systemically and collaborating across sectors to find solutions.
We've talked about making our buildings more efficient.
Right.
And finding cleaner ways to transport the goods we rely on. But what about the connection between those two worlds? How can we leverage those synergies to speed up the transition to a cleaner future?
That's a great question.
That's something for you to ponder.
Okay.
Thanks for joining us on another Deep Dive.
Until next time, keep learning, keep exploring, and keep asking questions.
Welcome back to the Deep Dive. We've tackled what's inside your building. But now, let's zoom out.
Okay.
That amazing stuff you bought, it got there via shipping. And that's a whole other carbon problem.
You're absolutely right.
Yeah.
We often forget about those massive cargo ships crisscrossing the globe. But they play a huge role in our everyday lives. And they have a significant impact on the environment.
Okay, I'm all ears.
Yeah.
But before we dive into solutions, paint a picture for me.
Okay.
Just how much energy are we talking about here?
All right.
What makes these ships such big polluters?
Well, get this.
Okay.
In 2023, fossil fuels covered a staggering 98% of international shipping.
Wow.
And the main culprit is heavy fuel oil.
Okay.
Basically the leftover gunk from crude oil refining.
So we're using the dirtiest, most polluting fuel imaginable.
Pretty much.
To power these massive vessels that carry everything we buy.
Yeah.
That's not great.
It's definitely not ideal. Heavy fuel oil is cheap.
Okay.
But it spews out tons of carbon dioxide, sulfur oxides, and particulate matter.
Yeah, that's not good.
And as global trade grows, so does the demand for shipping, which means those emissions could skyrocket if we don't change course.
Okay, so the alarm bells are ringing.
They are.
We need to decarbonize this sector, and fast.
We do.
But how do we even begin to tackle a problem this big?
Don't worry, there's hope.
Okay, good.
Several exciting technologies and strategies are emerging that could slash emissions from shipping.
Give me the good news.
Okay.
What are some of these solutions that could turn things around?
One of the most promising avenues is fuel switching.
Okay.
Instead of relying on that nasty heavy fuel oil, we can transition to cleaner options.
Okay, so what are the contenders? What fuels are vying to dethrone heavy fuel oil?
Liquefied natural gas, or LNG, is often touted as a bridge fuel. It's readily available. The infrastructure already exists in many ports. And it burns cleaner than heavy fuel oil, producing far fewer sulfur oxides and particulate matter.
So a step in the right direction, but maybe not the ultimate solution.
Exactly. While it's cleaner than heavy fuel oil, LNG is still a fossil fuel, which means it still releases carbon dioxide. And there's the problem of methane leaks during production and transport, which could negate some of the climate benefits.
Methane is a potent greenhouse gas, so we need to be mindful of those leaks.
Absolutely.
What about biofuels?
Yeah.
Could those be a contender?
Biofuels have a lot of potential. They're made from renewable sources, like crops, algae, and even waste materials.
That's cool.
And if they're sustainably sourced, their life cycle greenhouse gas emissions are significantly lower compared to fossil fuels.
So instead of burning ancient fossil fuels, we're using plant power to move those goods around the world.
Exactly.
I like it. But I'm guessing it's not that simple.
Yeah.
Are there downsides to biofuels?
One of the biggest challenges is scaling up production.
Okay.
We need huge amounts of biofuels to decarbonize shipping. And there might not be enough land to produce it all sustainably.
That makes sense.
Plus, there are concerns about competition with food crops and potential impacts on biodiversity.
Right. We need to make sure we're not creating new problems while solving old ones.
Exactly.
So biofuels could be part of the solution.
Right.
But we need other options, too.
We do.
What about those buzzwords I keep hearing? Green hydrogen and ammonia. Are those just hype?
Okay.
Or could they actually be game changers?
Green hydrogen and ammonia are definitely generating a lot of buzz.
Okay.
And for good reason. They're produced using renewable energy sources, making them truly zero-emission fuels.
Okay. I'm intrigued. Break it down for me.
Sure.
How do you actually make green hydrogen and ammonia?
Green hydrogen is produced by splitting water molecules into hydrogen and oxygen using renewable electricity, a process called electrolysis.
Okay.
It's like using sunshine and water to create fuel.
Wow.
And ammonia is a fantastic way to store and transport that hydrogen.
So we're basically using renewable energy to create a fuel that can power those massive cargo ships without polluting the planet.
You got it.
That sounds like something out of a sci-fi movie.
I know, right?
But I'm sure there are hurdles to overcome, right?
Of course. Right now, the biggest challenge is cost.
Okay.
Green hydrogen and ammonia are still more expensive to produce than fossil fuels.
Right.
But as the technology improves and production scales up, those costs are projected to drop significantly in the coming years.
It sounds like we need to be patient.
Yeah.
But the potential is huge.
It is.
And I imagine it's not just about the fuels themselves, right?
No.
We also need to consider the ships and the infrastructure at ports around the world.
You're spot on. Decarbonizing shipping requires a holistic approach.
Okay.
We need to make ships themselves more energy efficient, optimize shipping routes and speeds, and develop the infrastructure for refueling with these new fuels.
It's a massive undertaking. It sounds like we'll need collaboration on a global scale.
Yeah.
Governments, industry, researchers, everyone working together.
Absolutely. It's a complex challenge, but it's also an incredible opportunity to create a more sustainable and resilient global economy.
We've covered a lot of ground today.
We have.
From the nitty-gritty of building systems to the grand challenge of decarbonizing global shipping.
It's been quite a journey.
It's amazing to see how all these pieces fit together in the bigger picture of building a more sustainable future.
It really is. And it highlights the importance of thinking systemically and collaborating across sectors to find solutions.
Couldn't have said it better myself. Well, that's all the time we have for today, folks.
Yeah, thanks for listening.
You've heard about making our buildings more efficient.
Right.
And finding cleaner ways to move those goods we all rely on.
Absolutely.
But what about the connection between these two worlds?
Yeah, what about that?
How can we use what we learned to speed up the transition to that cleaner future?
Good question.
That's something I'll leave you to ponder.
Yeah, give it some thought.
From slashing emissions in our buildings to cleaning up those giant cargo ships.
Right.
We all have a role to play.
We do.
Thanks for joining us on another Deep Dive.
Until next time.